what comes to mind when we think of the term energy? Maybe a plug in the wall, or a strong punch, or maybe even a big explosion. Well, these are all examples of energy. And in physics terms, energy is the ability to do work. Energy, which is measured in joules, comes in many forms. This can come in gravitational, kinetic, potential, thermal, electrical, just to name a few. But today, we'll mainly be focusing on kinetic and gravitational energy.
Bro, what are you doing?
Bro, I have a date later. I need to make sure my breath doesn't smell.
Oh, alright. Wait, I kind of don't understand work, and I'm not prepared for next week's test. Can you explain work to me?
Well, work is just the change in energy. So we use the formula W equals F cosine theta times distance. So that would mean the three factors that affect work are angle, displacement, and force. Alright, okay, I'll explain it with an example, okay? So this shopping cart is 32 kilograms with the Mentos, right? So if I push it 5 meters, and the final velocity at the end of the 5 meters is 0.5 meters per second. Let's see. There we go, right there. If my final velocity here is 0.5 meters per second, we can plug that into a kinematic equation, find the acceleration, and then plug that into our F net equation, and find that our net force is 0.5 newtons. If we plug that into our work formula, then we'll find that the total work I did over this 5 meters was 4 joules.
Thanks, man.
I like to think of energy as the ability to do damage. So let's look at some different scenarios and see how much energy we can produce. Gravitational potential energy is the energy an object possesses due to its location relative to a lower position. Let's compare the gravitational potential energy of this eraser when using the floor as a reference point versus using this bottom floor as a reference point. As you can see, if I drop the eraser here versus if I drop the eraser here, we'll have greatly different gravitational potential energy and we'll do different amounts of damage. Now let's compare the gravitational potential energy of this eraser and this water bottle. Which one would you rather have fall on your head? You can see that the heavier the object, the more gravitational potential energy, the more damage it'll do. Now let's look at kinetic energy, which is the energy an object possesses while it's in motion. The formula for kinetic energy is EK equals 1/2 times mass times velocity squared. Let's see how this formula works. If a frisbee is thrown lightly at me, it will produce less energy than if a frisbee is thrown really hard at me. From this, we can see that higher velocity results in higher energy. Additionally, kinetic energy changes based on mass. We can see this difference by comparing me getting run into by my friend Jeremy versus me getting run into by my friend Alan. We can see that as mass increases, kinetic energy increases. Now, let's connect these two concepts of gravitational potential energy and kinetic energy by introducing this concept called the law of conservation of mass, which states energy cannot be created or destroyed, it can only be converted into new forms. Right now, I'm about to bike down this hill. The hill is 14 meters long and has an angle of elevation of 30 degrees, meaning that I am 7 meters elevated above the ground. My bike and I together weigh about 67 kilograms, meaning that right now we have a gravitational potential energy of 4,596 joules of energy. If I bike down the hill, or if I roll down the hill, my kinetic energy at the bottom will be equal to the gravitational potential energy at the top in a perfect world. And since we know my kinetic energy at the bottom of the hill was 4,596 joules, we can find that my velocity was equal to 11.71 meters per second. remember how I mentioned that only in a perfect world is the gravitational potential energy at the top equal to the kinetic energy at the bottom? Well, this is because in the real world, whenever energy switches forms, some of it is always lost. But let's not say it's lost. Let's say it's converted to less useful forms.
3, 2, 1.
Before we revisit the bike example, let's quickly introduce an idea called efficiency, which just measures how much energy is lost during a process. Efficiency is found by dividing the useful output by the input.
Go.
Let's look at the bike example again, while factoring in friction to find the efficiency. Let's start by drawing a free body diagram. Ideally, the gravitational potential energy at the top is equal to the kinetic energy at the bottom, and that will be our E in. Let's first find the value of our force of gravity, and use that to find the y component of our gravity vector. We need this, as it is equal to the normal force. From research, the coefficient of friction of rolling rubber on grass is 0.002. Using this along with the normal force, we can find that the force of friction is 1.137 newtons. We then plug this number into the work formula to find that friction does 15.918 joules of work in the opposite direction. Using this to calculate E out and percent efficiency gives us 99.65% efficiency and 0.35% loss. Now that we've learned how to calculate different forms of energy, let's look at two scenarios where I take varying amounts of times to go up the stairs. If we work out the energy I generate in each scenario, we'll find that I actually generate the same amount of energy. If you think about it, if I take 1 millisecond to go up these stairs versus taking 10 years to go up the stairs, I'll still generate the same amount of energy. So how do we distinguish between these scenarios? By calculating something called power, which represents the change in energy over time. Plugging these two situations into the power formula now shows us the full story.
Wow, that was fun.
I'm gonna reward myself by jaywalking across the street and buying a snack from the grocery store.
Oh no! A car is about to hit me. Let's apply what we've learned and calculate the energy generated by the car hitting me. Let's see, that's a 2016 Honda Civic, which weighs 1,245 kilograms. The car is traveling at around 14 meters per second, so that works out to around 120,000 joules of kinetic energy. Now, considering the driver's on their phone, they'll slam on the brakes for the final 5 meters. Now, the coefficient of friction of sliding rubber on concrete is 0.75. Using the normal force, we find that the friction has a force of around 9,000 newtons. Multiplying this by 5 meters, we find that the friction does 46,000 joules of work in the opposite direction, meaning the car will hit me with around 74,000 joules of kinetic energy on impact, resulting in a percent efficiency of 61.85%.
Bro, you good?
Oh, dude, I just got hit by a car.
Oh my.
Wait. I can't die yet though. I need to talk about the energy sources of that car. So, that car was powered by petroleum. And petroleum powers the car by heating the petroleum and causing gases to expand. Those gases expand and put pressure, which convert into mechanical energy, which make the car move. Now, if we think about how energy is changed in that process, it goes from chemical energy to heat energy to mechanical energy. Undergoing so many changes in energy means that we're going to be losing a lot of energy to other things. So, the burning of petroleum is only 30% efficient. Imagine if that car that hit me was electric. 60% of electricity in Canada is generated through hydro energy. Hydroelectricity is a renewable energy resource, as water will always keep on flowing. Hydro energy harnesses the natural flow of water and forces it through narrow corridors, which further increases the power. When this mechanical energy of water flowing goes through generators and creates electric energy, we see that there's only one change in energy. This means that hydroelectricity has an efficiency of 90%. We still have to mention though the downsides of hydroelectric energy, which is displacement of people who live in the area and disruption of wildlife. We should compare different energy sources not only based on their cost effectiveness, but their efficiency and renewability.
Yo, what are you doing?
Oh, I'm getting a thank you card for the viewers of this video. How does this sound? Thank you. Thank you for listening to my video. That was so thoughtful, so special, and so appreciated.
Thank you for listening.
Thank you.